So chapter 2 is on the algebraic eigenproblem. We're going to focus first on applications so we can get a really good idea and a good intuitive feel for why eigenvalues and eigenvectors are so important in various applications in science and engineering. To start with, let's think about a geometric transformation. So if you think back to chapter 1, we talked about A, U is equal to B. A being the coefficient matrix, which was known, U the solution vector that we're looking for, and B the right-hand side vector, which would also be known. We're solving for the unknown vector U. But later in the chapter, we talked about how that same mathematics could be interpreted differently, interpreted as a linear transformation. So AX is equal to Y, as we have here. So you have a vector X pointing in some direction. You pre-multiply by now a linear transformation matrix, and that gives you another vector Y, which points in another direction. So that linear transformation could accomplish various things. It could stretch the vector, make it shorter, it could translate it, it could rotate it, it could do various things to that vector. We want to look at it in this chapter from a geometric point of view is those special vectors for a given matrix that only get stretched. So they don't get translated, rotated, or any other transformation, they only get stretched, either longer or shorter. Now, sounds like a mathematical novelty, right? But it turns out that those special vectors that have this property have applications all over the physical sciences and engineering, as we'll see. So again, let's take a look at a geometric example similar to the one we started with in chapter 1. You'll remember there we had 2 points, which we represent as vectors from the origin to each of the 2 points. And we were looking for the matrix that transforms between them, the coordinate system between those 2 vectors. So here we're going to do a similar idea, but with a slightly different objective. And what we're going to do is start with the same 2 vectors. We're going to look for vectors that only get transformed to be longer or shorter. And the stretch factors will be the eigenvalues. So the first one will be stretched by 2. The second one will be stretched by a factor of 1/3. So here's the starting points x1 and x2 in some coordinate system. And we want to find the 2x2 matrix A that transforms each of those vectors into just a stretched version of themselves. So mathematically, that means that x1, when pre-multiplied by the matrix A, which we don't know yet, will return the same vector x1, just scaled by a factor lambda 1. Same thing for x2. So x2 gets transformed to itself by the same matrix A, and it's just longer or shorter based on the value of lambda 2. So if we write that out, we have these 2x2 systems here. Again, this is x1, gets transformed to x1 by the scale factor 2 here, and we're looking for the 2x2 linear transformation that accomplishes that stretching. We're looking for the same matrix A that also transforms this vector into itself with the scale factor lambda 2, or 1/3. And again, the argument is that these are somehow special, which we'll discuss in more detail. So we have 4 equations for 4 unknowns between these 2 systems. So we can solve for a unique solution for A11, A12, 21, and 22, and get the matrix that does this transformation, that has this special property. Now that is special because if you take any other vector with the same A matrix, and you say A times X, it will not produce the original X. It will produce another vector that's been, again, translated, rotated, maybe stretched, but not just stretched. So these 2 vectors are very special with respect to this matrix A in that geometric sense. So this is the eigenproblem, where we get the eigenvalues and eigenvectors. Now in this case, we actually kind of did it backwards. So I gave us the eigenvectors, x1 and x2. We had the stretch factors, those are the eigenvalues, 2 and 1/3, and we were looking for the matrix A that produces those as the eigenvalues, eigenvectors. Normally it's going to be the reverse. We'll have the matrix A, and the question will be what are the eigenvalues and eigenvectors of A. Another example, a physical example in this case, is that of principal stresses and principal axes in continuous media. So if you have a solid or a fluid of some sort where the properties change continuously throughout the medium, you have a stress state. Every point in that medium has a stress state. The stress state is given by a stress tensor. The tensor can have up to 9 components, and they include normal stresses, which are perpendicular to a surface, and shear stresses, which are tangential to a surface. And I won't go through the details here. The derivation is here if you're interested, to show how this physical question ends up being mathematically answered by getting the eigenvalues and eigenvectors. We'll actually do an example in the next video of this in a 2x2 context, which will make it easier. But for now, let's just think about that vantage point. The vantage point that I look at, that continuous medium, for which I have this stress tensor. The question is, can I look at it from a different vantage point? Can I change my coordinate system such that the stress tensor changes in some advantageous way? For example, would it be possible for me to look at it from just the right vantage point so that there's only the normal stresses and no shear stresses? Those are called the principal stresses, the normal stresses, and the principal axes are the directions, which only give us normal stresses. So you may remember Moore's circle from an undergraduate strength of materials class or mechanics of solids class, which is kind of a geometric way to represent that fact. So I want to emphasize again here, the question from a physical point of view is, what is the stress state that only has normal stresses? So what is that vantage point? So that's a physical question. The mathematical answer to that question is, what are the eigenvalues and eigenvectors of the stress tensor? So we're going to see this all the time, where there's this interplay between the physical, the geometrical, and the mathematical. Same is true for moments of inertia. Moments of inertia are encapsulated in a tensor, and you can find the principal moments of inertia and so forth in just the same way. Another application that's going to occupy a lot of our time in Chapter 2, because it's so important to us as scientists and engineers, is that of solving systems of linear ordinary differential equations. So these are basically dynamical systems. A dynamical system is just any system that evolves in time. It could be a mechanical system, chemical system, biological system, electrical system that evolves in time. We have to distinguish between discrete systems and continuous systems. A discrete system is a system that has discrete particles or discrete masses and objects, so springs and masses, for example. A continuous system is one where the mass is distributed throughout the medium. And so that would be like a solid or a fluid, as we just discussed a moment ago. So for a discrete system, and in this case a discrete linear system for now, we'll talk about nonlinear systems at some point, but for now let's just think about discrete linear systems. We can encapsulate the dynamical systems governing equations in terms of a system of first-order linear ODEs of this form. So A here is a coefficient matrix that comes from the physics of the system. U is the state vector that we're looking for. Those are the dependent variables that we want to find. They might be positions, they might be angles, currents, whatever the case might be. And F is a known forcing function. It's a vector that encompasses known forcing terms. The dot here on the left-hand side, that's du dt. So anytime you see a dot, that's just a shorthand for a time derivative. So we have du dt is a coefficient matrix A times u plus f. And we want to solve for the dependent variables. So these could be capital N equations where n is 1, 2, 3, up to hundreds or even thousands or millions. So we want to be able to solve this big system, potentially big system, that are coupled. The equations are coupled together. So I can't just solve for u1 and u2 separately. I need to solve for them in a coupled fashion. This is called the state space representation, this first order form. So the approach we're going to take, and we'll introduce this in a couple sections, is what's called diagonalization. And the idea behind diagonalization is I have this difficult problem, u dot is equal to au plus f. Can I simplify that problem in some way? Can I introduce a new coordinate system or a new set of variables with respect to which the system is somehow simplified? So the ultimate simplification would be, can I uncouple the equations? So they're coupled in terms of u1, u2, u through un. Can I come up with another set of variables with respect to which the system is uncoupled that would be awesome. That would be great. That would simplify the problem tremendously. We can solve each equation individually, one after the other, and we'd be done. So that's actually done through the process of diagonalization. So we'll see how that works shortly. The key, though, is, and so you're thinking, well, where do the eigenvalues, eigenvectors come in? They come in because the matrix that does that transformation, we call it the modal matrix, for reasons you'll see in a later video. That modal matrix that does the transformation that uncouples the system of equations is comprised of the eigenvectors of the coefficient matrix A as the columns in the modal matrix. It's quite amazing, actually, and so we'll see how that all plays out. There's additional applications all throughout science and engineering. These algebraic eigenproblems just pop up everywhere, where the eigenvalues and the eigenvectors have some physical meaning. And it can literally mean the difference between life and death. If you've ever seen the Tacoma Narrows Bridge collapse in the early 1940s, there's actually a YouTube video that shows this. Yeah, they had YouTube in 1940 apparently. So you can see how catastrophic the effects of some of these things that we'll talk about can be. So let me just mention some additional applications, some of which we'll see in more depth. You can see the references to later sections when we'll discuss these. So every system has natural frequencies of vibration. So this is the proverbial, opera singer singing at just the right tone that corresponds to the natural frequency of the glass, and the glass breaks. So every system, again, mechanical, electrical, biological, every system has these natural frequencies, these special frequencies that excite this resonant behavior within the system. So that's a physical question. What are those natural frequencies? And the mathematical answer is you need to know the eigenvalues of the system. Stability is another very important topic. So these same dynamical systems, there the question is, if I were to tickle the system, if I were to give that system a little bit of a nudge, tiny little nudge, what'll happen? If it's stable, nothing happens. Whatever little disturbance I introduce just dies out and everything is fine. If that little disturbance, however, grows and gets amplified, then the system is unstable. So we're often very much concerned with the stability of our dynamical systems. Once again, stability, physical question, mathematical answer is related to the eigenvalues and eigenvectors. Towards the end of the chapter, we'll be talking about some very important matrix decompositions, such as singular value decomposition, SVD, QR decomposition. These are essential decompositions that allow us to take a matrix and decompose it, separate it out into various pieces. And we do that either to solve a system, to diagnose some aspect of that system, or to better represent the system in some way. And so we'll see a number of examples, SVD and QR being two of the major ones. Quadratic programming is a type of optimization problem, and it turns out that it boils down to simply solving an eigenproblem. Numerical methods. So many numerical methods are iterative. So you have an algorithm that you repeat over and over and over again. You guess a solution. You do this algorithm over and over again. And hopefully, as the iterations progress, your approximate numerical solution gets closer and closer to the correct solution. Of course, the question is, how do you know that that's true? How do you know that your iterative process is going to indeed converge towards that correct solution? Turns out the question, numerical method, does it iterate properly? The answer is you need to know the eigenvalues of the iteration matrix. That's a subject for chapter 6. There's another decomposition, proper orthogonal decomposition, we discuss at the end of the book in chapter 13. It's very useful, very powerful for taking large data sets and extracting out useful information from that data set. It's used in many, many different applications across the sciences and engineering. So what you'll notice about some of the things I've said will kind of hint at some common features across these applications. And one of those is that the eigenvectors in some way provide a transformation. So in the case of our geometric example, it's a transformation that only stretches the vectors. In the context of principal stresses and principal axes, it's a transformation with respect to which we only have normal stresses and no shear stresses. In some of these other applications, such as the system of linear ODEs, we're changing the coordinate system, we're transforming the system such that the equations are all uncoupled. So always think about, if you're kind of getting lost, where's he going with this? We're getting into the details, into the weeds, and I'm getting a little confused. Stop and think about, why are we doing this? What is the simplification that's happening? What is the simplification through the modal matrix, through finding the principal stresses and principal axes? What is that simplification in this particular context, and how is it related to eigenvalues and eigenvectors? In part 3, where we focus on optimization, we're going to find that there's a lot of situations in optimization where the goal is really to find an optimal basis, a basis being like a glorified coordinate system, a way to represent a system. And that system can better be represented, more easily be solved, interpreted, and so forth by using some eigenproblem, whether it's algebraic, as we're discussing now, or a differential, as we'll be discussing in Chapter 3.